desk. So is my lecture slide visible to you?
Yes, sir, it
Yes,
is
sir.
visible.
Okay, fine. So before starting today's lecture, okay, so let me make some announcements. Okay. Uh, I'm not, I won't be able to take, okay, two lectures, okay, in the week of 20th week, okay. So 20th and 22nd, I won't be able to take lectures. I'll be traveling that week, okay. Okay. So anyhow, I'm conducting, okay, presentations on Saturday, 30th October. So that way I think, okay, you will get enough time to prepare, okay, term paper report and presentation. Okay. So you utilize that week, okay, to prepare your term paper and term paper report and presentation. Okay. So I'll try to compensate, okay, as much as possible, okay, the missed lectures by taking these presentations on the Saturday. Okay. So Saturday, make sure the 30th of October, I think it's Saturday. So make sure that you are available, okay, entire Saturday. Okay. I want to finish presentations, okay, term paper presentations as much as possible on, okay, Saturday, 30th October. I think any pending things, I think left out things will be taken in following lecture, one of the lecture, okay, that week. November first week will be taken, some of the um, presentations. Okay. So please mark your calendar. Okay. So there won't be, okay, MM681 lectures on 20th and 22nd of this month. So you know that 23rd there is a quiz 3 exam. 23rd October there is a quiz, okay, 3 exam which will be conducted similar to what we have done quiz 2. Okay. Is it clear? The announcement what I have made. Okay. So,
Yes, sir.
yeah. Okay. So we started having discussion about fatigue, cyclic plastic deformation, so in this course, okay, basically we are going to discuss about microstructure evolution under cyclic plastic deformation. Okay, so we are not going deep into the fatigue deformation of materials, that there are dedicated courses on fatigue of materials. So, and also I used to teach earlier, okay, off semester course, okay, off semester fatigue, off semester creep and superplastic, full semester course basically. That's also elective used to be. So in actually I won't be able to teach two electives, so I restricted myself to teach this plastic deformation microstructure evolution. So there actually in the earlier another course which I used to teach, there actually off semester like almost, okay, around 20 lectures devoted for the fatigue deformation of materials. Okay, 20 hours lectures. But here, actually, in this course, I'm just giving some important aspects of fatigue behavior of materials, cyclic plastic deformation of materials, which basically we are touching information related to how microstructure is going to evolve during plastic deformation under cyclic loading conditions. Okay, so in my previous lecture, I think we had, I think, defined the what is fatigue. Okay, typically what you're talking about metal fatigue. Okay, fatigue behavior of materials, metallic materials, okay, which basically related to failure of premature failure of material or damage. It can not necessarily be failure, can also can damage of the component subjected to repeated loading. Okay, and it's a repeated loading, this can lead to, which can be related to repeated application stresses or strains, that varying the stress or strain. Okay, so if you vary the stress, automatic obviously strain is going to vary. If you define the strain limits, stress also going to vary accordingly. Okay, so the definition of fatigue is like this. We had discussion about it, and in order to understand fatigue behavior of materials, one has to do, okay, for a material, for example, you have developed a new material, how this material is going to behave under cyclic loading conditions. So one has to establish, okay, some methodology to understand fatigue behavior of the particular material. Okay, so there are different approaches people use. One is called stress life approach, other one is a strain life approach, And the third one, fracture mechanics approach. Okay, stress life approach and strain life approach basically involves taking a tensile specimen and subject material to either changing the stress limits or strain limits. Either change the stress limit or a strain limit. Okay, respectively called stress life and strain life approach. Okay, and monitor, okay, total number of cycles required, okay, for the specimen to fail under the given set of, okay, stress conditions or a strain conditions. So we call, if you use stress conditions, it's called stress life approach, and strain life approach basically related to strain. Okay, varying the strain limits. Between strain limits, subject the component or specimen. Okay, between the strain limits. So life means actually how many number of cycles are required, okay, or the material has experienced before its failure. It's basically called fatigue life. Okay, once you define a strain amplitude or a stress amplitude, for that given stress amplitude or strain amplitude, how many number of cycles are required for its failure. Okay, so that is called fatigue life. Okay, so fracture mechanics approach is basically related to, okay, crack. Already assume that this crack has been initiated. In the, take this kind of CT specimen, compact tension specimen, and we already initiate some crack. Okay, so crack has been initiated. Now we will understand how the crack is propagating. Okay, so what kind of, okay, the toughness of this, indirectly we are talking about toughness, but under cyclic loading conditions. Under cyclic loading conditions, how the crack is going to propagate. Okay, so after how many number of cycles, the crack is basically leading to failure of the component. So that is called fracture mechanics approach. So in my previous lecture, we had discussion about stress life approach, which was actually designed by, proposed by Wöhler. Okay, Wöhler was the first one who has actually designed an equipment which basically can induce, okay, idealized stress conditions, and one can, okay, see that, okay, by applying different stress amplitudes, we can monitor how many number of cycles the material is experiencing before its failure. Okay, the coming to strain life approach is most popular, okay, as compared to stress life approach. Okay, for mechanistic purpose, if you want to have better understanding about fatigue behavior of materials, people use, okay, strain life approach. But actually steels, if you talk about steels, okay, most of the steels have been studied, okay, by using a stress life approach, which basically related to high cycle fatigue. Stress life approach can be used for understanding high cycle fatigue. Strain life approach is mostly used for understanding low cycle fatigue, but it can also be used for understanding high cycle fatigue. Okay, so high cycle fatigue involves most of the material, okay, most volume of the material undergo elastic deformation under high cycle fatigue. Okay, in case of low cycle fatigue, okay, major volume of the material is going to undergo, okay, plastic deformation. Okay, so that is the difference between high cycle and low cycle fatigue. People have expressed mathematical equations to describe high cycle fatigue and low cycle fatigue. High cycle fatigue, it can be described by using a Baskin equation, which basically relates by stress amplitude or strain amplitude with respect to number of cycles to failure. Okay, similarly, okay, Kaufman-Munson also uses, okay, expresses how the strain amplitude, okay, varies with the number of cycles to failure. So one is for the high cycle fatigue, other one for the low cycle fatigue. So if I want to know where the transition is going to happen, I have to equate these two terms. Then I can get where is the transition from low cycle to high cycle fatigue can take place. Here, B, C, epsilon F prime, sigma F prime, these are material constants. Depending on material to material, we may see slight change in the transition number of cycles required from low cycle to high cycle fatigue transition. Okay, so I think then actually we had, okay, I think one important discussion. I think we had, some students have discussion about, okay, we had a discussion about strong, okay, tough and ductile material, how it is going to behave. Okay, if I construct a SN curve, okay, it can be stress life curve or strain life curve. Okay, how these three materials are going to behave. Okay, for example, here I've taken a, when I say strong, means that I'm talking about high strength material. When I say low strength, okay, ductile means mild steel, low strength material. Medium strength steel, I'm talking, okay, in terms of, okay, tough material, relatively tough as compared to high strength and mild steel. So if I take these three materials, okay, so typically, okay, in under high cycle fatigue regime, in a high cycle fatigue regime, okay, if I make a horizontal line, okay, high strength material is going to behave better than, okay, low strength material. Okay, as compared to, look at it in high cycle fatigue regime, high strength steel going to behave better than, okay, mild steel, which is a low strength. In case of low cycle fatigue regime, it's going to be opposite. Okay, so typically, we are what we are going to see. Okay, so brittle sorry, if you talk about high strength steels, like a strong materials, are going to behave less. Okay, less going to have less fatigue resistance as compared to low strength materials. Okay, because this regime is related to plastic deformation. This regime is related to okay, elastic regime. So if we have a good amount of ductility, okay, we can see the number of cycles required for the complete failure of the component is going to be more. Okay. Similarly, another example, if I take a steel, one has been normalized by heat treating the material to austenite temperature and cooled by in air. Okay. In other thing, you heated the material to austenite temperature, quenched it rapidly. That basically gives a martensitic structure. Other one gives a assume that I have a medium carbon steel. Within medium carbon steel, we can get a perlitic steel plus perlite plus ferrite. In quenched one, we will get a martensite. Okay, because martensite steels are hard in nature as compared to normalized steel. So accordingly, we do see high cycle fatigue regime. In a high cycle fatigue regime, hard material behave better. The performance of fatigue performance of hard materials better than normalized soft materials. It is going to be opposite when you talk about low cycle fatigue. So one has to be cautious while selecting a material for a given application. We have upfront we have to know the particular component how many number of cycles that it is going to experience. Okay, and is there a plastic deformation? That means the stress is actually higher than the yield stress or below the yield stress. Accordingly, you have to select material. Okay, material selection for low cycle fatigue is different than high cycle fatigue performance. Okay, is it clear? Any doubts here? Am I online?
Yes, sir. Sir, actually, sir, can you please explain why, sir, it was that Martin side have that less cycle fatigue?
See, if we talk about low cycle fatigue, the cracks, easily can be initiated, can easily be initiated, The already are subjecting this material to above yield stress. That means plastic deformation is going to take place. Okay, so the plastic deformation, is a crack has been already initiated. Okay, crack because of plastic deformation, crack has been initiated. The crack propagation, is very fast. Okay. Because is first of all in a martensitic steels it's very easy to generate more cracks as compared to a normalized steel. Okay, the martensite laths, if we talk about, which have a stress risers, which are the sharp edges. Okay, the laths or plates, whatever see, will act as a stress risers. So that we are going to create very easily cracks. The crack can be nucleated very easily and can also be propagated very fast because we have a limited ductility in a hard martensite material steels. In case of normalized steels, the crack, whatever already as we initially assume that first of all number of cracks are less, that even that cracks will not propagate very easily. There is a crack blunting is going to take place. Okay, so crack propagation is also going to be controlled. Okay? So that is the where actually the explanation here for the low cycle fatigue. When you talk about high cycle fatigue, in high cycle fatigue, what you are talking about, we need to have apply high strength, to initiate, because we are talking about, we are talking about we need to have a higher strain amplitude or stress amplitude. Then only we do see initiate the crack, because we already discussed the period for crack initiation is more than a crack propagation in high cycle fatigue regime. Okay, so in case of hard materials, the strength already we need actually higher stress to initiate a crack. Okay, the stresses might not be, if for example you apply this much stress, the stress is not sufficient to initiate the crack in. Okay, so we'll talk about why even within elastic deformation also we do see crack formation. Okay, that will be discussed down the line. Okay, so even if the materials are both of them are in elastic deformation, I always say major or most of the volume will be under elastic, but that means there is something which also undergoes plastic deformation, locally. Okay, so that it means for the crack to initiate, we need to apply high strain or high stress in case of a quenched hardened steels as compared to normalized steel. Is it clear? At least this will be clear, for you, all of you. Okay, am I right? So this
Yes,
low
sir.
cycle fatigue regime is very clear for, because crack is going to initiate in all of them because already giving enough stress or enough strain amplitude. So that can take care of initiation, crack initiation. Okay. But in, first of all, the crack initiation is more in the quenched steels as compared to the density of cracks are more in case of quenched steel as compared to normalized steel. At the same time, the crack propagation is going to be fast in case of hardened steels as compared to normal steels because there is a plastic deformation, significant plastic deformation take place that can blunt the cracks. Okay. So in case of, okay, you will understand soon. Okay, in the low cycle, so in the high cycle fatigue regime, okay, in order to initiate a crack, okay, in high strength materials, we need to apply some, because there is a stress concentration. We need to apply some minimum stress. Then only we do see crack initiation. So that it requires high stress is required for crack initiate the cracks. Okay, in hard material, martensite steels as compared to normalized steel. Okay, any doubts here? So then I think initiated discussion on constructing stress strain curve under cyclic loading conditions. Under cyclic loading conditions. So we subject the material, okay, to given strain amplitudes. Okay, define the strain amplitude. I define my strain amplitude. Okay, and change the strain amplitudes and construct a saturated loop for each defined strain amplitudes. Okay, then connecting the locus of each saturated loop, okay, we get a, okay, stress strain curve under cyclic loading conditions. Interestingly, if I take cold work material and, okay, annealed material under monotonic conditions, okay, we do see there is a significant difference in the stress strain curve. Okay, but if I say these two materials, we subject them individually, separately under cyclic loading conditions, we may, what will happen? The okay, annealed material is going to get cyclically hardened, whereas cold work material cyclically hard, okay, softening take place, cyclic softening and cyclic hardening take place. That may bring, okay, the curves, okay, happening. Okay, cyclic deformation will be different. That's why, okay, that way. So if I take a anneal material which can get strain hardened, okay, that can undergo cyclic hardening. In case of cold work material, it already has a enough dislocations. Okay, so those can undergo cyclic softening because of, okay, annihilation of the defects that can take place. So that can, with the persistent slip bands can form very easily. So that can lead to reduced strength under cyclic loading conditions. So this is for polycrystal. In case of a single crystal, okay, typically, okay, we'll get this kind of loops. Okay, so we have only, there's no grain boundaries. Okay, so we don't see much initially strain hardening. Okay, we do see almost, okay, constant stress per hour length of time. Okay, where whatever dislocations have been generated, those are going to get realigned. Okay, so that can lead to formation of persistent slip bands. Then after certain amount of, okay, further deformation, the bands again, okay, lead to additional, okay, dislocation generation. So that can lead to dislocation cell structure. Okay, so in a typically, if we deform a material, okay, we deform a material, it can be single crystal or polycrystal. Typically, one of the characteristic feature of the microstructure evolution is formation of persistent slip bands. Okay, in case of single crystals, okay, and we do see apart from persistent slip bands, we do see some kind of veins, bundles, kind of, okay, loops can form. In polycrystals, we directly, okay, we do see persistent bands. Okay, we may not see veins, bundles. So labyrinth structure can be developed. Okay, combination of persistent slip bands plus, okay, dislocation cells together, which will call labyrinth structures. Okay, so this can form in both single crystal as well as polycrystal. Okay, so these are examples. Okay, in some materials, okay, it was shown. Okay, in a single crystal, when you deform, we do see this kind of, okay, veins kind of structure. Okay, in single crystal, initially low amount of, okay, deformation. If you go to some certain amount of deformation, we do see formation of persistent slip bands. These bands are going to form, which are actually relatively low dislocation density regions as compared to matrix. This is a matrix, and this is a band, persistent slip band. Again, the matrix, and this is a persistent. So the persistent slip bands is nothing but rearrangement of dislocations, where the annihilation, when you deform material in different direction, we are changing the direction, positive and opposite direction. In that case, what happens? Annihilation of defects can take place very easily in certain locations. That can lead to formation of a nice bands. Okay, those bands are called persistent slip bands. Okay, so combination of persistent slip bands locally some places. Okay, and also this cell structure may give you like a, okay, labyrinth kind of structure. Okay, so this is the kind of characteristic microstructural features what we see if the material has undergone cyclic loading, plastic deformation. Okay, So this is one of the, okay, if you see in a microstructure at high magnification, okay, if I say formation of this persistence slip bands, that means we can say that a particular component has undergone cyclic plastic deformation. Okay, is it clear? I think I stopped at this moment in my previous lecture. If there are any doubts, please let me know before proceeding further. No doubts. Okay. So if you are interested, I think there's a dedicated course which is, I think, running. I guess I'm not sure. Okay, Professor Aparna Singh teaches this course. So there is a dedicated, very nice book by Subhash Suresh. Okay, so I think there are so many books. Okay, this is one of the books which basically most of people refer. Okay, to have a better understanding of the fatigue of materials. So today I'm going to discuss, okay, something about, okay, how the crack is going to get initiated, how the crack is going to propagate, okay, under cyclic loading conditions. Okay, now crack initiation. Okay, so what can lead to crack initiation under cyclic loading conditions? Any idea?
Stress concentrations
Yeah,
notches
stress.
are available.
Yeah, so because stress concentration is always can lead to a crack initiation. Okay, the stress risers can be a two types, can be internal stress risers, can also be a external stress risers. Okay, when I say internal stress risers, any examples for internal stress risers in the materials? Typical stress
Foreign
risers.
material segregation, sir.
Okay, particles, if we talk about any particles, inclusions. Okay,
Dislocations, density, particularly in some specific places.
dislocation density is not really, okay, we cannot call it as a internal stress riser. Okay, because there is not really concentration. Okay, if cell structure forms, we don't see, kind of, it will not act as a stress riser. Okay,
Stacking faults,
yeah, basically defects like, okay, grain boundaries, twin boundaries, faults, okay, can give, act as a locally okay, intrinsic, these are intrinsic stress risers. Okay, coming to external stress risers, in examples, external stress risers, external stress risers.
change in area,
Surface, we talk about roughness. Okay, if you have a lot of roughness, okay, if there is some, okay, something sitting on the surface, okay, or design fault, okay, because if we put a lot of sharp cutters, okay, those will act as a those are basically external stress risers. Okay, so crack can be initiated because this is a fracture mechanics approach. Okay, whenever there is a stress concentrating region, okay, stress risers basically, okay, can lead to formation of a crack in the material. So these are actually common, okay, whether it is a monotonic loading or cyclic loading. Okay, we do see external stress ranges and internal stress ranges. Assume that, okay, I have given a single crystal, okay, and there is no stacking faults, no inclusions, okay, and the design was perfect. There is no sharp corners. Okay, there's very nice, very smooth polish, subjected to fatigue cyclic loading condition. Even then, the material fails. Okay, did you get my point? What I'm saying? Because crack, okay, fracture, okay, crack or fracture basically involves crack initiation, crack propagation. Whether it's a monotonic or cyclic, whatever loading, so stress rises will play a role. Now assume that I have given a material which is a single crystal, which doesn't have any inclusions, which doesn't have, okay, any particles, okay, and the component also very nicely designed. There's no, okay, stress concentration at any point of time. Even then, the material is going to fail miserably, okay, under cyclic loading conditions. Okay. Can anybody say why it fails? Because I said there are
Because
no,
of tensile stresses in half of cycle.
which one? Tensile stresses?
Tensile stress will be there.
I'm giving, okay, I'm deforming material below elastic deformation. Assume that, okay, below, within elastic deformation, below yield point. Any idea?
When we do cyclic loading, maybe locally bonding will break and it will initiate as a void.
Yeah, I think you're close to that. Okay, so the one of the, I think, important thing, okay, all these, okay, whatever the last four factors what we discussed is a common, okay, whenever there is fracture in the material. Okay, but under cyclic loading conditions, so there is a activity called cyclic slip activity. Cyclic slip activity is going to, okay, take place. This cyclic slip activity can generate can generate, okay, stress risers, can generate stress risers during, okay, deformation under cyclic loading conditions. Okay, so what is meaning of cyclic slip act? So I think the other things, okay, everybody's known thing. Okay, I think we already know. Okay, all these things, okay, stress rises, internal, external stresses can lead to. There is also internal stress rises. So all these things can lead to crack initiation. But what I'm talking about under cyclic loading conditions, we do see cyclic slip activity. The slip activity can lead to formation of internal stress rises. Okay, what is the meaning of cyclic slip activity? Okay, okay, assume that at a certain location, okay, at a certain location we may see some stress concentration, okay, is going to develop. Okay, so how it is going to develop? Okay, see, when I deform a material plastically, okay, assume that, okay, though I'm deforming it below yield stress, okay, at certain location we may see, okay, the stress can rise locally, okay, which can lead to plastic deformation. Okay, when you apply plastic, when there is a plastic deformation, that means that there is a shearing activity taking place. Okay, so at the surface, okay, when I deform a material, we take a material, single crystal, okay, single crystal. If I deform it, okay, around, okay, the loading direction, now I applied a stress to maximum peak stress. Okay, when I apply a stress to maximum, so during, okay, plastic deformation basically involves shearing activity. So this shearing activity, okay, at the free surface, okay, is going to generate some new fresh surface. Okay, when I decrease the stress, okay, when I decrease the stress, okay, and, okay, decrease means actually I'm applying, okay, decreasing, I'm applying stress in other direction now. Okay, so when I'm decreasing stress in and applying stress in other direction, okay, assume that I'm applying tension compression. Okay, so what happens again? This surface now shearing activity happens other direction. Okay, now again if you have do, okay, again we do see, okay, shearing activity, opposite. Okay, now what we are seeing actually, depending on, okay, stress, pressure, compression, tension we are applying, I do see this kind of slip activity locally at certain location. Okay, at near some surface, okay, we are going to see slip activity. So this slip activity, that's what we are talking about, cyclic activity. Okay, we are changing the stress, okay, high to low, low to high. Okay? So that can lead to, okay, local slip activity. So that can give rise formation of a, okay, we are going to see formation of slip bands. So that can lead to a, okay, near the surface, what we are seeing here, okay, there is a, okay, some kind of, okay, intrusion is going to form. Okay, intrusion is going to form in the material if the, okay, initial slip activity happens in this direction. If the slip activity happens in other direction initially, I'm going to see, okay, extrusion kind of defect. Okay, we do see extrusion kind of, okay, defect is going to form. So if these things form, okay, then local, what you are seeing now, it becomes act as a, now it's like a locally void. Okay, this can lead to, okay, this can act as a stress riser for the further crack to initiate. Okay, so the cyclic slip, whenever there is a cyclic slip activity in the material, so that can lead to formation of intrusions, and or extrusions. Okay, depending on, okay, which direction is happening, the shearing activity, that can lead to intrusions and extrusions in the material. Okay, under cyclic deformation. So those now become a crack initiation sites. Okay, this act as a stress rises in the material. Okay, so what we are seeing, the formation of intrusion extrusions can eventually lead to persistent slip bands at high magnifications. If you go to high magnifications locally, I do see formation of persistent slip bands in the material. So if I take a tensile specimen, okay, first very, okay, I polished it very nicely. If I do cyclic slip activity, I do see formation of this on the surface. I do see formation of these marks. Okay, if I go to a little bit high mag, I do see, okay, kind of, okay, in valleys and hills kind of thing. Okay, valleys. So the valleys basically called intrusions. The cracks what we are seeing, okay, these are like valleys. These are called intrusions. Okay, and what we are seeing kind of hills, those are called extrusions. Okay, formation of intrusions, extrusions is also because of cyclic slip activity. This is another characteristic feature what we can see, okay, during cyclic deformation of a material. Is it clear?
Sir,
Yes,
these
sir.
stresses that we are applying, should it be completely reversed type of stress, sir? That
Not
means
necessary. Not necessary. Not necessary to be, okay.
It can be always be tensile itself.
Tensile tension also can be there. Okay, tensile tension, okay, tension compression. Okay, there are different types of cycles which I did not discuss here. Okay, but which I discuss in another course. Okay, different types of cycles. Okay, in MM733 I will discuss, okay, about different types of cycles, what you see, what you encounter. Okay,
Okay.
in all the, because this stress not necessarily tension compression also. Okay,
Okay, sir.
So this will be a surface phenomenon only, or in
yes,
between also.
fatigue always, okay, fatigue crack always gets initiated at the surface.
Okay.
Surface preparation is very much important. Okay, so fatigue is the surface phenomenon. Okay, the surface is the most dangerous spot for the crack to initiate under cyclic loading conditions. Okay, so this is how actually this is another microstructural feature, though it's okay different magnification we talk about. Okay, okay, we may see this formation of hills and valleys on the surface that basically indicates that there is a cyclic deformation activity happen on the material. Okay, so I said, okay, even, okay, even if you apply stress, okay, even if I apply stress, okay, my applied stress is actually below the yield stress, below the yield stress. If I assume there is a minute crack, okay, now whatever crack has been initiated, okay, so that crack, okay, okay, can lead to, okay, further, okay, deformation to happen around the crack region. Okay, what is meaning of stress riser here actually, and from a fracture mechanics approach. Okay, now actually we have seen, okay, like for example on the surface you have seen this kind of, okay, intrusion. Okay, or sometimes we may see internal losses, some because of some inclusion something happens, we may see some crack formation, crack has been initiated. Okay, so the crack tip, okay, at the in front of crack tip, okay, the stress is going to be less than sigma naught or greater than sigma naught. How much it is going to be? Any idea? At the crack tip, okay. Now I'm applying, okay, in a, for a bulk material, I'm applying a sigma naught. Just assume that the stress is relatively lower than, slightly lower than the yield stress of material. Okay. So no, actually, okay, some slip activity happens, cyclic slip activity happen in some places, okay, because the stress, okay, in some of the, okay, look, direction, some of the angles, the stress is sufficient to initiate, okay, yielding in the material. Micro yielding can take place. Micro yielding can take place. Okay, so once micro yielding takes place, that can lead to cyclic slip activity. So that can lead to formation of a intrusion or extrusion. Okay, now assume that there's a kind of, okay, crack has been formed, okay, on the surface. Okay, now if I look at the stress at this, okay, in front of, okay, in front of a crack tip, okay, it is going to be higher or lower than the sigma naught. I hope some of you already, okay, had fracture mechanics course, okay, something in your UZ level.
Higher, sir.
Okay, that basically is a higher, always depends on the radius of curvature of, okay, crack tip. Most of the time the crack whatever forms is, okay, if it is a sharp, that is your radius of curvature actually, okay, is going to different than if it is a blunt crack. Am I right? Okay, so near the, okay, crack tip, the stress can be infinity also if it is a very sharp tip. The crack tip is very sharp. Okay, your stress, okay, though I'm applying sigma naught, okay, assume that there's a inside, just to concentrate in center crack. Okay, so around this crack, okay, the stress is going to be very high. Okay, near the crack tip, it can be infinity also, okay, if it is a very sharp tip, depending on, okay, sharpness of a tip, the crack tip, okay, the stress magnitude is going to change. Okay, though I'm applying a sigma naught, which is just below the yield stress, okay, I'm going to see if there is a crack already present or already some has been initiated, okay, during deformation. What happens? We do see so much plastic deformation can take place around the crack tip. Okay, so the stress is going to be much higher, okay, at the crack tip, depending on sharpness. So the magnitude of stress is going to change at the in front of the crack tip. So one can estimate, typically people, okay, estimate sigma, okay, the stress, okay, okay, in front of the crack tip, okay, is basically how much stress you're applying sigma naught a, okay, size of the size of the crack, okay, so of the size of the crack a, and rho t, radius of curvature of the crack tip, okay, whole about 1 by 2, okay, this, okay, basically tells how the stress is going to vary, okay, when you change the, depending on the crack size, depending on the okay, radius of crack tip. So sharper the tip, we do see, okay, the stress is going to be higher, okay. So that means actually that if I assume the crack has been initiated or already present in the material, that is bound to propagate, because we are going to see, okay, very high stress locally, okay, and also locally we see a lot of plastic deformation can take place around the crack tip, okay. So that's how actually the materials fail under cyclic loading conditions, even if the applied stress is just below the yield stress, okay. One cannot expect, okay, so much of plastic deformation, but we may see some micro yielding that can lead to cyclic plastic silk activity, okay, that can also generate cracks, or already if cracks are present, like a polycrystalline materials grain bond is already there, so we do see cracks can initiate, okay, that now the crack can be very easily initiate the boundary, so that can lead to easy propagation, okay. So this is how actually the cracks, okay, are going to play a role, okay, or in any stress rises whatever present, that can lead to, okay, the stress is going to be higher, so that can lead to failure of the component under cyclic loading conditions, okay. So this is basically stress concentration from the cracks what we are going to what you have learned so far, okay. So now crack has been initiated now, okay. So how this crack is going to get propagate under cyclic loading conditions, okay, crack propagation, okay, how it is going to have, okay, take place. So this slide basically, okay, shows how the crack is going to propagate under cyclic loading condition. Now assume that after certain number of cycles the crack has been initiated. Assume that after certain number of, okay, I applied so many cycles, after certain number of cycles crack has been initiated. How this crack is going to propagate, okay, during further cycling, during further cycling. Now assume that this is a crack, okay, if crack is like this shape, okay. So now I applied stress from A to B. When I apply stress A to B, okay, what happens? The crack front, whatever is there, is going to be sheared, pulled. Okay, there will be some shearing activity take place in front of the crack tip. Okay, so this crack front, okay, is going to move, okay, because of plastic deformation. Okay, we are applying some stress, so there is some shearing activity taking place. We are going to see, okay, because around the thing, the stress will be very high, so that can lead to plastic deformation. That means shearing activity is taking place, so that's going to pull the, okay, for example, it's going to pull the material, okay. So this shearing activity can pull the crack front. When I apply stress to C, okay, when I apply the stress to maximum stress, okay, it is going to bulge like this. The crack front is going to, the sharp whatever I think is going to bulge like this, okay. Once, if I drop the stress from C to D, okay, again you're going to see shearing activity in opposite direction. The shearing activity is going to take place in opposite direction, okay. But already what happened, crack has been moved from here, okay, from this location to here, okay. When I drop the stress, when I'm applying stress in other direction or drop the stress, okay, to minimum stress, we are going to see the stress, okay, shearing activity is going to take place in opposite direction. That can lead to, okay, some blunting. Crack can get blunt, okay. But what happened, okay, when it comes down to E point, okay, it can become still, okay, sharp, because the blunting, a lot of blunting has taken place again, okay. Finally, okay, the front has been moved from one location, this location to, okay, this location. This much movement has taken place when you apply a, it's like this cycle, one cycle, okay. So I applied stress to, okay, minimum to maximum and maximum to minimum, okay. The crack front has moved, okay, due to local plastic deformation shearing activity, so we do see the bulging, okay. Then reverse direction, when you drop or applying minimum stress, that time we do see some kind of, okay, blunting kind of thing, okay. Then we are going to left with an extended crack, okay. So this is how actually, okay, one cycle can lead to crack front is going to move one certain amount of length, Okay, depending on stress, how much stress you are applying, okay, that changes, okay, the front movement, how much front, okay, extension has taken place. So this, okay, one can summarize in different, okay, like this. So, okay, usually crack opening, okay, crack at maximum load, and crack is going to get crack closed. Okay, finally crack has been closed, but at the same time, the crack front has moved certain length, okay, extended certain length. Okay, this whole process is called plastic blunting process. Plastic blunting process for crack growth. The mechanism what it has proposed, okay, is basically called plastic blunting process for crack growth under cyclic loading conditions. Okay, is it clear about the crack? Because initially we had discussed of crack initiation, now crack growth under cyclic loading. Is it clear?
Yes, sir.
Okay. So this crack propagation, okay, can lead to certain microstructural features. Okay. So the crack, okay, has, for example, you have taken a component which has failed. Okay. If you see, okay, formation of this kind of, okay, beach marks, okay, this is an indication, okay, okay, this is an indication that, okay, the material has undergone cyclic, okay, loading conditions. The material was subjected to, the component was actually subjected to cyclic deformation. Okay, so by looking at fractography, okay, with a naked eye, okay, even with a naked eye, we are able to see like a beach marks. Okay, we are able to see beach mark kind of shape. Okay, so this basically indicates that one can say the material has undergone, okay, cyclic or fatigue, okay, failure. Okay, this is how people do investigation. Okay, a particular component, how it was failed, whether it's failed due to fatigue loading conditions or a monotonic loading conditions or something else. Okay, or shearing activity, okay, like the people do by looking at the fractography. With the naked eye, one can see this okay, beach marks. If I go to, okay, SCM level fractography, okay, we do see, okay, formation of within a grain. Okay, for example, within a grain we do see formation of this kind of, okay, marks. So these marks are called striations. Okay, so each striation from one to one, okay, that basically indicates the crack has been propagated, okay, for each cycle. Okay, crack propagation basically we already learned. Okay, the crack front moves for each cycle. Okay, so that within a grain, okay, one by looking at how many number of striations are there, people can say how many number of cycles, okay, the material has experienced for the crack to propagate. Okay, so these are the microstructural features which indicate that the material or component failed due to cyclic loading conditions. Okay, is it clear?
Yes, sir.
Okay. Yeah. So this is how actually, because I'm connecting microstructure evolution under cyclic loading conditions. Okay. So the another important thing, okay, because we always talk, okay, fracture mechanics approach is also important thing. Okay. One has to, okay, understand how the crack is propagating. Okay. How the crack is propagating with number of cycles. So fracture mechanics approach is basically what it involves. Take a compact specimen and monitor, okay, the initial small crack, how it is propagating, how it is propagating with given stress, okay, amplitude or stress range. Here, for example, when I say stress range, sigma minimum, sigma maximum, and sigma minimum, stress amplitude by 2. Okay. Here, for example, I given two different, okay, stress ranges, two different stress ranges. Okay, one sigma, so delta sigma 2, assume that greater than delta sigma 1. Okay, it's obvious that, okay, if the stress amplitude or stress range is more, okay, the number of cycles to failure is going to come down. Am I right? Okay, if the stress range, okay, is more, okay, that is going to bring down the number of cycles to failure. Okay. So what people do by just, okay, for example, at a given, stress range, monitor how the crack is propagating, okay, with number of cycles, with number of cycles. So with increasing stress range, okay, with increasing stress range, okay, the number of cycles to, okay, propagation is going to come down because you are giving more stress. Okay, so that basically the propagation will be faster. Okay, so if I take, for example, okay, two different, okay, at any point, between any 2 points, okay, the crack propagation rate, okay, under cyclic loading condition is basically given by dA by dN. dA by dN. Okay, so the slope, okay, if we take if we take 2 points, adjacent points, if we get a slope, okay, the slope basically called, okay, how the crack length is changing, okay, as a function of number of cycles. So dA by dN is called crack growth rate under cyclic loading conditions. So people do establish, okay, crack growth rate, okay, for different materials, okay. For example, here, okay, so by taking a stress intensity factor range, okay, delta K, okay, basically we know the stress intensity factor is K is equal to some geometric function sigma square root of pi A is the crack length, okay. So this is how it basically stress intensity factor is known from a fracture mechanics approach. And delta K basically delta sigma, okay, we are basically delta K basically delta sigma square root of pi A. Okay, so with respect to stress intensity, because we are changing the, because under cyclic loading condition, I'm giving delta sigma or sigma A. Okay, sigma A is nothing but delta sigma by 2. Okay, so in the cyclic loading conditions, we need to talk stress intensity factor range, because we are changing the stress minimum and maximum. Okay, and monitor how the crack growth, okay, is taking place, okay, for different stress intensity factors, okay. So if I look at here, okay, initially there won't be any crack growth, okay. After certain theoretical some kind of, okay, threshold, after giving some threshold delta K, okay, we start seeing the crack growth is going to start taking place. Okay, so initially we have a stage, okay, regime 1, okay, regime 2, and regime, there are 3 regimes, okay, as a function of how the crack growth rate changes as a function of stress intensity factor range. Okay, we do see typically, okay, the material are going to behave, okay, exhibit like this. A particular material can exhibit this kind of, okay, sigmoidal shape curve. Okay, so initially we do see slow crack growth followed by a almost, okay, power law kind of thing we do see. Then again we do see rapid, okay, crack growth is going to take place. So higher the stress intensity factor range, the crack growth rate is higher. Okay, if the stress intensity factor is very small, okay, the crack growth is going to be very slow. So an important regime, okay, for understanding fatigue behavior of material, people do establish, okay, this power law behavior. Okay, so this power law behavior is basically we are talking about, okay, dA by dN crack growth rate, okay, equal to C delta K to the power of sometimes N, people say sometimes M. Okay, most commonly most of the textbooks use M. Okay, so dA by dN is equal to C delta K by M. Okay, so this, okay, equation was proposed by, okay, Paris, a scientist called Paris. That's why it's called Paris law. It's called Paris law. Okay, this is what our equation derived. Okay, for this, the power law behavior. Okay, okay, you consider, okay, this is going to be the crack growth under cyclic loading conditions is going to depend on stress intensity factor range to the power of M. M is a Paris exponent, C is a coefficient. Okay, so if I want to know dA by dN, now actually if I put this delta K here, okay, it's going to be M. Now if I want to know, how, okay, how many number of cycles are required for the crack to propagate from certain length to certain length. Now for example, I initially crack length is A0. Okay, it has been extended to some length A1. I want, okay, this much crack length. Okay, how many number of cycles are required? What do you do? See, for example, now actually I know crack growth rate is basically, okay, given from the taking Paris law. You just assume that it's in the parabolic law, okay, the regime 2. Okay, now I wanted to know, okay, how many number of cycles are required, okay, for the crack to propagate from A0 to A1, okay, or A1 to A2. Okay, what should I do? Because there is A here, okay, there is A here.
Integrate.
Integrate, yeah, you need to integrate. Just go take the D and that side, bring this one here, okay, and integrate it. I can get how many number of cycles are required, okay, for the crack to propagate from certain length to other length, or actually other way also. Now I given this many number of cycles, okay, now if I increase the number of cycles to this much, what is my crack length change? Okay, how much crack length is going to change? Okay, So if I know, okay, this behavior, okay, because I'll come to know, okay, at what stage, okay, the material is going to fail. So that means most of the times we do not allow, okay, a component to fail, okay. So we have to do these calculations, okay, up to what crack length, okay, or up to how many number of cycles the material can be the component can be used. After that you have to stop, okay, or replace the component with some other material. So the material should not go to this rapid, okay, the component should not go to a rapid, okay, unstable crack growth regime. So it has to, if it is within this regime, then it's fine, the component is safe. Okay, that's how actually people, okay, establish, okay, using this Paris law, one can estimate, okay, one can understand, okay, how many number of cycles are required for the allowable crack length. Okay, is it clear about this? Is the fracture mechanics approach, okay. The importance basically of this approach is basically you can know, okay, how much crack, okay, length is allowed, okay, for a given application, so that the crack will be in still, okay, at least the stable regime. Is it clear? Okay, so if I look at, okay, some standard materials, steel, titanium, aluminum, okay, so typically, okay, we'll get, okay, like this, okay, depending on delta, okay, depending on strength of material, okay, we do see that the delta k is also going to change. For example, the threshold what you are seeing, okay, is going to be higher for steel as compared to, okay, titanium, as compared to aluminum, okay. So this is how actually people for different materials people establish, okay, this kind of, okay, curve in a lab scale, okay. Then we can understand how this particular material is going to behave under cyclic loading conditions. Okay, so that is basically, this is whatever I wanted to discuss as a part of this course, okay. I think related to fatigue or cyclic plastic deformation. So this is why okay, I put a full stop for the cyclic plastic deformation. I just taken a major, okay, important aspects, okay, which are related to cyclic plastic deformation, and I spend little bit time on how microstructure is going to evolve under cyclic plastic deformation. Okay, the characteristic features what we see if the material has been subjected to, okay, cyclic loading conditions. Okay, one what we see, if the material has failed, that means actually it will have the fracture surface if it has with a naked eye, if it has a beach marks, that's one indication at a macro level. If we go to little bit micro level, fractography, if we do, I do see striations. Okay, and if I go to little bit, okay, if I look at just on the surface itself, okay, with little bit of low mag, we do see formation of intrusions, extrusions. That's also indication of material has undergone cyclic, okay, loading conditions. Okay, undergone cyclic loading conditions. And if I go to much higher magnifications, okay, formation of persistent slip bands at a TEM level, okay, we do see formation of persistent slip bands. That is the most important characteristic feature that says that material had undergone cyclic loading, okay, deformation. Okay, so that's about the fatigue cyclic plastic deformation of materials. So please let me know if there are any doubts before proceeding to next topic.
Cyclic loading means that loading cycle will be positive, negative simultaneously, sir, like that, or
It is not necessary to be positive, negative, okay, because we have to have a minimum maximum stress. Okay, when I say, for example, I said, okay, stress range, if you talk about, okay, minimum stress and maximum stress minus minimum stress is called stress range. That means the material, okay, when you deform material or component when it's undergoing, okay, there should be fluctuation in the stress or fluctuation in the strain. Okay, that's the definition itself. I said repeated application of, okay, stress or strain. It can be positive, negative, okay, can be within positive also, can take place, okay. So there is called, okay, there's a called stress ratio. Okay, stress ratio is nothing but, okay, sigma minimum by sigma maximum. Sigma minimum by sigma maximum. That's called stress ratio. The stress ratio can be, okay, -1 to 1. Okay, can be, okay. Typically -1 to 1. When I say -1, what does it mean? Sigma minimum by sigma maximum is equal to -1. What does it mean?
Sir,
One is
both are same value, but one side it was negative.
yeah, that means one is in tension, other one is in compression.
Yes,
If I apply a cycle, okay, so the cycle is like exactly sinusoidal, okay, idealized sinusoidal curve. Okay, I said it can be the value can be -1 to 1. Okay, if it is a 0.3, okay, if you assume the R is equal to point stress ratio R, okay, is equal to 0.3, what does it mean? Both of them are in
Positive.
tension. Both of
Yes,
them are in tension. Or okay, can be also compression, but it's cancelled. So usually, okay, compression is very rare to see fatigue behavior. So at least we need to have a tensile component, but crack to get opened up. Okay, so we always need some tensile component. So if it is R is equal to 0.3, what does it actually? We are applying everything, both of them in tension. Okay, but there should be a fluctuation. There should be a kind of fluctuation should take place. Okay, then only we do see cyclic, that's called cyclic loading conditions.
Sir, actually one more thing, sir. By increasing that surface finish, okay, without changing any yield strength of the material, can we increase that life of the material,
Yes,
sir?
yes, that's called one of the important, okay, surface preparation. Okay, surface roughness plays significant role. Okay,
So
rough,
normally,
rough,
how much we can use, sir? Normally, industry people we are doing around 96 for turning, sir. By using
you
that
have to
level.
remember that. Okay, this is like a surface roughness, like a fractal. Okay, depending on at what level you are looking at. Okay, so there is no, okay, we never get a, okay, I did, okay, very nice, because always atomistic level also we do see some rough, okay, surface. So it depends, okay, at what level of magnification you're looking at the roughness. Okay, ideally we never get a, okay, perfectly smooth surface. Okay, I think if you learn about fractal, okay, there we talk, okay, go to deeper and deeper, we do see rough surface is going to present. Okay, only thing, the magnitude is going to change, the roughness magnitude is going to change. Okay, so if there are people have established, okay, the smooth surface finish, okay, diamond polish, if I go for, okay, that can have a better, okay, improved fatigue performance than the, okay, only if you have only rough oxide layer. Okay, after oxide deoxidation, if I do, you'll get some rough surface. Okay, that surface, because that is going to be detrimental for the fatigue. So the level of roughness, okay, can influence the fatigue behavior of a material.
Okay.
Is it clear? Usually smooth, because we never do smooth we cannot go to, for example, component, we cannot do diamond polishing. Okay,
Yes, sir. That cost will be.
yeah, so you can never get, okay, so it is subjected to, okay, so people do some kind of cleanings, acid cleaning, so that, okay, so put it in, so that you can get minimize the roughness as much as possible.
Okay.
Okay, so in the other MM733, I will discuss about the factors which can influence. Okay, here I don't talk much, okay, because here actually we have a lot of content to be covered. Okay, at the top of it, actually, I have to say only how the microstructures are actually evolving. Okay, so that's basically the theme of this course: plastic deformation and microstructure together. Okay, so I'm just giving some important aspects related to plastic deformation and how this can lead to a, okay, microstructure evolution in the material. Is it clear?
Yes, sir.
Okay, so the next important topic, okay, so I do say everything is important because I'm covering only, okay, the plastic deformation is a huge component, it's a huge subject. So I'm just taking some important concepts related to plastic deformation. So the next one, thermally activated plastic deformation of metals. Thermally activated plastic deformation of metals. So can anybody say what does it mean? Okay, that name itself should indicate, okay, should, any idea what does it mean?
High temperature plastic deformation.
Okay, it's not necessarily high temperature. Okay, temperature assisted. Okay, it's a temperature assisted thing. Okay, so there will be plastic deformation can be activated. Okay, that means thermal, okay, process, some thermal process can assist the stress, applied stress, for the plastic deformation of metals. So plastic deformation of metals is a dynamic in nature, considered as a, the plastic deformation metals is considered as a, okay, dynamic in nature. What is meaning of dynamic in nature? time dependent. Okay, it's a plastic deformation is a time dependent process. Okay, in 1925, okay, there's a scientist called Becker, okay, who has indicated, okay, there will be some thermal, stresses, in terms of thermal vibrations, thermal, temperature changes can assist the applied stress for the plastic deformation to take place. Okay, so these two, okay, so I think this dynamic nature is basically coming, okay, because of some thermal fluctuations which basically assisting the applied stress, so that actually we can overcome obstacles which are present in the material. Okay, so plastic flow basically related to dislocation movement, okay, slip activity, gliding activity, what you're talking about. Okay, so the dislocation activity, the dislocation movement can lead to a plastic flow in the material. Okay, so the dislocations while moving, okay, from one location to other location in atomic level, okay, there will be a some resistance to the dislocation motion. Okay, we already discussed, okay, there will be inherent resistance of a crystal to the dislocation motion. What is that inherent resistance is called? We already discussed there is an inherent resistance by the crystal, okay, for the dislocation motion.
Pierre Navarro
Yes,
stress.
Piles Navarro stress, that basically the stress required to to overcome that inherent resistance of the crystal to the dislocation motion is basically Piles Navarro stress. Okay, basically energy in terms of it, okay, Piles Navarro energy. If you convert into stress, Piles Navarro stress. Okay, that is one of the, okay, that's a within a atomistic level. Okay, we are talking about, okay, within just within less than, okay, within atoms with 2 3 atom, okay, diameters itself, we do see there is inherent resistance. Okay, apart from this inherent resistance, okay, there will be some obstacles. We do see some obstacles present in the material. Okay, those obstacles also, okay, resist the plastic deformation. Okay, that resist the movement of the dislocations. Okay, so those, okay, obstacles, okay, are, okay, important, okay, which basically control the deformation, plastic deformation of a material. Okay, so these obstacles, okay, are actually of two different types, or of two different types. Okay, so some obstacles, okay, will have long range stress field, long range stress field. Some obstacles will have a short range stress field. Some obstacles have a short range stress field. Okay, assume that I have a crystal, okay, some material, okay, in that we have a some obstacles. Some obstacles can be having a long range stress field. Some obstacles will be having short range stress field. When do you say long range stress field and short range stress field? Long range stress field basically related to at least, okay, minimum, okay, 10 atomic diameters or more. Okay, the obstacle size what you're talking about, okay, the obstacle size what you're seeing, if it is more than, okay, 10 atomic diameters. If you take a particular material, we know atomic radius of a particular metal. Okay, so at least, okay, diameter, you can say diameter 10, okay, 10 atomic diameters, okay, size has to be there. That basically involve long range stress field. If the, okay, the obstacle size is basically less than 10 atomic diameters, okay, that basically involves short range stress field. Okay, so if I talk about, okay, I need to, okay, I said actually these are two different, okay, obstacles are going to present. So this long range stress field, okay, cannot be overcome by, okay, thermal fluctuation. Okay, that means thermal stress fluctuations, if you give some thermal change, okay, temperature change, that will not, okay, overcome the, okay, long range stress field obstacles. So those barriers are called athermal barriers. Those barriers are called athermal barriers. Whereas, okay, these short range stress field obstacles, okay, which can be overcome, that means actually some applying some thermal vibrations, some thermal fluctuations, that can assist your applied stress, so that that can be overcome very easily, okay, by thermal fluctuations. So those are called thermal barriers. Thermal barriers. So these thermal barriers, okay, can, okay, lead to, okay, So basically we are talking about, okay, two types of barriers now. One is a thermal barrier, next one is a thermal barrier. Okay, so these barriers basically control the plastic deformation, but one of them can be overcome with applying some thermal fluctuations. That those are called thermal barriers, which cannot be overcome by temperature change, thermal changes. So that is those are called athermal barriers. Okay, so in 1925, Becker has mentioned, okay, strain rate, okay, is basically, okay, can be given in this, okay, Arrhenius equation, in the form of a Arrhenius equation. Strain rate is equivalent to some frequency factor mu exponential minus delta H sigma by kT. Okay, this H sigma, okay, what H of function of a sigma, it's called enthalpy or also called activation energy of plastic deformation. Activation energy for plastic deformation. K is a Boltzmann constant, T is a temperature on absolute scale. Okay, so look at here. Okay, this H sigma is a decreases with the applied stress. Typically, the activation energy going to come down with increasing applied tensile stress. So the thermal barriers, okay, which can be overcome by thermal fluctuations, can lead to, okay, can assist the, okay, deformation is very easily. So that process is called thermally activated plastic deformation of metals. So what does it mean? Thermal barriers, if they are present, by giving some thermal change, temperature change, can be overcome. Okay. So the activation is nothing but, okay, the energy required to overcome a barrier. Okay. For example, now I have a complete. This is my total barrier. Is okay. The biggest barrier actually is, okay. This plus this one together is a, okay. This much I need to apply this much stress. Then only I can overcome the, okay, barrier, total barriers. Okay, assume that, okay, in a material I have some long range stress fields and also short range fields. Okay, so the total stress required, okay, to overcome, that means to initiate the plastic deformation material, I need to apply a tau naught stress. Then only, okay, I do see plastic deformation is going to take place. Okay, out of tau naught, okay, tau mu, okay, is basically, tau mu is basically the stress required to overcome athermal barriers, required to overcome, okay, athermal barriers. Okay, and tau star, okay, if tau star, if I take stress required to overcome, okay, thermal barriers, that means total stress required tau naught is equal to tau mu plus tau star at any given temperature. At any given temperature, the total stress required to, okay, to initiate the plastic deformation of material, plastic flow in the material, I need to apply tau naught. That basically is equivalent to tau mu, okay, stress related, stress to overcome the thermal barriers plus stress to overcome the, okay, thermal barriers. Okay, so this, okay, is going to the stress required, okay, now at a 0 Kelvin, if you take a 0 Kelvin, okay, where there is no temperature, okay, so 0 Kelvin, okay, so what we see at a particular strain rate, if a deformed material, okay, here I've taken two different strain rates, okay, gamma 1 dot and a gamma 2 dot, okay, these two different strain rates. So these two strain rates, increasing strain rates, okay, so at a 0 Kelvin, at a 0 Kelvin, I need to apply a tau naught stress. With increasing temperature, with increasing temperature, okay, with increasing temperature at a given particular strain rate, at a particular strain rate, okay, this stress, the stress required to overcome, okay, thermal barriers is going to come down, but the stress required to overcome this, okay, a thermal barrier is not going to change. Okay, after certain amount of temperature, the stress required to overcome all the thermal barriers is going to be zero. That means I need to apply only stress required to overcome the, okay, thermal barriers. Okay, so depending on strain rate, higher the strain rate, I need to have a higher, okay, thermal stress. Okay, your, okay, thermal stress is not going to change, only thermal stress is going to change depending on the strain rate. Okay, is it clear about the thermal and thermal barriers and the stress required to overcome, okay, these barriers is basically can lead to a plastic. Once you overcome, that means actually you can initiate the plastic deformation very easily.
Sir,
Okay,
at 0 Kelvin, why we need to apply maximum stress?
why do you need to apply 0 Kelvin? Because there's no thermal activation. Okay, that means I need to apply, for example, at 0 Kelvin, I need to assume that this is a stress field I have in the material. Okay, these are by long range stress field, and these are short range stress field. These are maximum. Okay, this is the biggest, okay, barrier. Okay, if I compare, okay, look at the biggest barrier. So I need to apply it or not, because there's no thermal activation. The moment once you apply some temperature, thermal fluctuations can assist the applied stress. That means actually your stress required, okay, to overcome, okay, thermal barriers is going to come down. Depending on temperature, your stress requirement is going to come down, because temperature also assisting, okay, fluctuation, whatever thermal fluctuation also assisting. Some of the barriers
Okay,
can
sir.
be overcome, okay, by just giving a temperature. Is it clear about the thermal activation process? So far, I'm telling thermal and thermal barriers. What are thermal barriers? What are the thermal barriers related to plastic deformation? Can anybody give some examples for thermal barriers and thermal barriers? I said, okay, a thermal barrier involves a long range stress field, okay, which is related to at least, okay, 10, okay, 10 atomic diameters of size. The barrier it will be having 10 minimum, okay, 10 atomic diameters or more. Okay. In case of thermal barriers, the size of the barrier is less than 10 atomic diameters. So can anybody list down, okay, some thermal barriers and thermal barriers? No idea? Because we do see obstacles, okay, in a material which can cause, okay, which can resist the plastic deformation. No idea? No. Very strange, okay? Because material, if you talk about a material, okay, which of them can, okay, act as a speed breakers for the plastic deformation? We had so much discussion, okay?
Sir, in
Which, what is that?
patties, intermetallics,
Yeah, if we
Yes,
have any precipitates, okay, which are of like a
precipitates.
size, okay, greater than, because precipitate size, okay, greater than 10 atomic diameters, okay. If we talk about incoherent precipitates, okay, whose size actually will be greater than 10 atomic diameters. Okay, when the dislocation is coming, okay, when it sees a precipitate, it's going to stop for a while. Okay, we need to apply high stress to overcome that, okay, precipitate. So that is, okay, example for, okay, long range stress field, okay, a thermal barrier. Another example, if I see, okay, dislocation different planes, okay, different slip planes, okay, that, okay, it requires, okay, a lot of energy, okay, to overcome, okay, to undergo, to see the deformation in other direction, okay, another plane, slip plane. So dislocations on other slip planes, okay, is another example for a long range thermal barrier. In case of thermal barriers, can anybody give guess some thermal barriers which are of a small in size? Okay, the size of the barrier is small in size. No. Okay, Piles Navarro stress itself, okay, is one of the, okay, because we are talking about the atomic, okay, less than 10 or very within 1 2 atoms, okay, resistance will be there. So that can give 1 minute. Hello, yeah. So the thermal barriers is already given. Thermal barriers, okay, one is the best example is a Piles Navarro stress, okay, which basically involves in atomic level, okay, 2 to 3 atoms spacing only. Okay. And other thing, okay, forest dislocations. Forest dislocations, because dislocation is going to thread the gliding planes, going to thread the gliding planes. Okay. Forest dislocations, they are present. Those can act as a barriers. Lower cotton logs, which are also barriers, okay, which are of a small, okay, within atomic level, okay, those barriers. Okay, cross slip activity, if you see, okay, one plane to other plane, we are talking just within a, okay, the cross slip activities also can be also be thermally activated. okay, climb, okay, activate what you're seeing, okay, that also basically can be, okay, is thermally activated. Climb
Sir,
process can also be.
Hall patch constants can also be considered.
Hall pitch constant is not a barrier, okay, basically that way all these things can contribute to Hall pitch constant, okay.
Okay.
Barriers can constitute. What I'm asking, what are the thermal barriers what you see in crystals, in a crystalline materials, okay. So these are the thermal barriers what you are seeing, okay, overcoming piles and porous stress, intersection of forest dislocations. Basically forest dislocation can thread the dislocations, okay. Gliding, okay, gliding planes can be threaded with the dislocations, okay, which basically involves, okay, all kinds of, okay, barriers, lower quarter loss, all of them can control the by gliding activity and non-conserved motion of jogs, which are of a small atomic sizes, okay, cross slip activity and climb activity, all these things come under category of thermal barriers. That means which can be thermally activated, which can be by giving a temperature I can activate these things. I can easily activate this defect, these barriers. So these are called thermal barriers, okay. So this is another important. I just introduced a concept called, okay, active, because we already discussed activation energy and activation. Another important is called activation volume. Okay, the change in, okay, activation energy with respect to the shear stress is called the activation volume. Activation volume, okay. So the change in, okay, with applying stress usually, and okay, enthalpy or activation is going to decrease, okay. It's called, okay, this minus dh by d tau is called activation volume, okay. Each of these thermal barriers will have a particular activation volumes, particular activation volumes. So this table gives some indication, okay. For example, if I determine somehow some experimental technique, if I determine activation volume, okay, if it happened to be the determined value is happened to fall, for example 1 b cube, if it is between 1 b cube to 10 b, okay, 10 b cube, b is a Burgers vector, okay. I have some experimental technique to determine the activation volume. If the activation volume found out to be, if it is in the range of 1 b cube to 10, okay, 10 b cube, okay, that means it is a climb. Controlling the rate controlling process is a climb. If the activation volume is found to be between 10 and 100 b cube, okay, that means the deformation, okay, is having a rate control mechanism which is basically related to cross slip, okay. So by looking at, okay, so one can, for example, between cross slip and climb, which is a dominant mechanism, rate controlling mechanism, how do you assess? By determining the activation volume, okay. Activation energy also gives some indication, but activation volume can tell you, okay, what kind of, okay, rate controlling mechanism for a particular, okay, plastic deformation mechanism what you are talking about, okay. So whether it's a cross slip or climb which is controlling the overall, okay, plastic deformation of a material. So by just one has to determine activation volume. I'll stop it here. Okay, we will discuss in detail, okay, about some more things about the activation volume, how to determine activation volume, okay, and okay, this thing, okay, and how, what is the theoretical basis for the activation volume, we'll discuss in my next, okay, class. So if there are any doubts, please let me know. Now it's at 12:30, close to 12:30 now. Is it clear?
Yes,
Sir,
sir.
Yes.
so can we call grain boundary also as a thermal barrier? Because with increase in temperature, mobility of grain boundary also increases.
See, grain boundary, okay, yeah, if it is only, if it is small within, okay, that 10 atomic diameter is fine, okay.
Okay.
So typically if it is a, because we typically say 0.5 to 1 nanometer, okay.
Okay.
So if I take a material, okay, whose atomic size is, assume that, okay, 3 angstroms.
Okay.
So we are having a 10, okay, how many you are having atoms across the boundary?
So I didn't get your question.
If we assume my grain boundary width is 1 nanometer,
Okay. Yes.
how many atoms can be present in a grain boundary?
If the atom size is 0.1, then
No, yeah, assume the atom size is 3 angstroms. Yes.
3 angstroms. Okay.
How many
So
atoms?
33 atoms.
Okay, then can you call it as a
Okay. It's long range. Then it
yeah?
becomes. Okay. So
So could you please repeat this explanation? There was a lot of background noise. I couldn't
No, see,
particularly.
if I assume typically grain boundaries width is about 1 nanometer. Okay, if the atom size assume the 2 to 3 angstroms. Okay, how many atoms can be present in a grain boundary? In just okay one particular direction. Okay, how many atoms I can see in the width direction?
I'm not sure of this actually.
See, you don't know how many angstroms to is equal to nanometer.
Okay, like that.
But I think the other student also did miscalculation. Okay, is it a 30 atoms present?
No, sir, about 3 atoms.
Only 3 atoms are going to present. Okay. It is actually okay. 1 nanometer is equal to 10 angstroms.
Yes, sir.
Okay, okay. So in with one direction, okay, we are going to see okay only okay, 3 atoms. Okay, if we talk about other directions, okay, we do see plenty of atoms. Okay, so in one direction, okay, in with direction only, we can say it is okay. It can be activated thermally. Atoms can jump. That's what the frequency what you're talking about, atoms diffusion can take place. But if we talk about other direction, it's not a thermal barrier.
So,
Okay,
so how many atoms
we
would
need
should it
10
have for
atoms,
it to be
less than 10
considered?
atom spacing. Okay, less than 10
Okay.
atomic diameters.
Okay.
Then only it's called thermal barrier. Okay, so complete grain board is not a okay thermal barrier. It's only in one direction only is a thermal barrier. Other direction is not a thermal barrier. Any doubts? I don't know whether it's going into your mind or not, whatever I'm teaching. Okay. So
It was going, sir.
going in, okay.
Yes,
Then
sir.
it's okay. Maybe teaching very slow or fast or is okay pace that what
It
pace
is
I'm
okay.
teaching.
Okay, sir.
It is okay, sir.
Okay.
Actually, the duration makes that thing, sir. Actually, 1.5 hours, that is long
Mhm.
stretch. So that's it.
Okay. No, it's a no problematic or good. I'm not getting.
Actually, sir, you are telling us, sir,
Uh,
whether I am able to get it. So that long stretch hours that so the people at that end they are not able to tell what you are asking. So this the
okay.
thing. But
Okay.
we are getting, sir, whatever you teach.
Okay. Okay. Good. So I'll stop recording. Okay. If there are any doubts, actually students can stay back. Okay. Who has doubt? Stop recording.